So, continuing from where we have stopped, we talked about, just introduce the code test. So, let us see what is the code test. First of all, we go to drill the samples from the concrete. So, coring is the process. So, it is rotary drill, usually rotary drill what we use, right, and can be oil cooled or water cooled. It could be oil cooled or water, because you need cooling, So, coring can be oil cooled or water cooled, So, rotary drilling machine could be oil cooled, more commonly water cooled. Now, if you want to do chemical testing, water cooling has a, you can't use distilled water for cooling purpose. So, this kind water cooling can add contaminant. So, you have to see that if you are doing chemical testing, water cooling. So, you have to see that if you are doing some chemical testing or something of that kind, preferably with inert coolant one should be doing, which will not contaminate the concrete. Then important is the location and size. Now, size must be representative of the concrete, because concrete is homogeneous at a macro level. More you go finer, it becomes heterogeneous. And for example, in centimeter level, 1 centimeter level, in fact, it is heterogeneous, because you can have aggregate sizes larger than 1 centimeter, then mortar, and aggregate is from some parent rock. So, that will have its own inhomogeneity whatever is there, but that is relatively less inhomogeneous or heterogeneous. It is heterogeneous, rock should be heterogeneous at still micro level, the grains and so on, impurities, or what you call the the constituent chemicals in the grains, it might vary from point to point, etc., etc. So, that would bring in some inhomogeneity. In concrete, additionally the mortar is there. Mortar itself, if you look at it, if you consider sand particle, then it will be at fraction of a millimeter level, 0.8 millimeter or so. Sand sizes are 475 micron to 475 micron to, we consider it up to 4.75 mm to 75 micron. That is what we consider as sand. So, 5 mm, close to 5 mm and smaller. So, 1 millimeter level sand sizes are of that 0.8, 0.9 average, 0.8, 0.9 or 1 millimeter, that order would be there. So, there again it is heterogeneous, the sand and the hardened paste, and at the paste level again it is heterogeneous. So, I am not going to that part again, microstructure level. So, if you are taking a core, you are looking at the macro property. Compressive strength is a macro level property, as we understand. Therefore, you should take such size which is representative of the concrete as a whole, and you can treat it as a macro concrete. So, in that case, size is, I will just tell you, size will be related to its diameter or minimum dimension. Location, as I already told you earlier, you do not take from a vulnerable location, which will cause more damage to it, right. So, that is what it is. Drilling, I have already told you, drilling is rotary drilling. Now, when you drill, actually you drill from the top side, right. You drill from the, you will be drilling possibly from the top side, you will be drilling from the top side, right. This is what it is, top or surface, from the surface, vertical also you can drill. So, what you do is you drill it something like this, right, and there will be some undulation here. You have drilled it something like this initially. Then what you do, you simply shear it off by putting some sort of a, giving some sort of pressure like this or moment or something of that kind. You put a wedge or even a screwdriver does the job, and just break it. So, when you shear it, you will have this undulated. So, in fact, the piece you get may not be very polished at the surface, but surely you will be somewhat undulated at the bottom. So, what you do? You trim it, then you trim it here and might trim it up also. So, this is called trimming. So, after drilling, trimming, and there has to be a minimum size, because as you would see a little bit more, the measured strength is a function of this L, and if this is D, function of L by D. So, below a point of length being too small compared to D, results would, you would get a variable results. I mean, you do not want that way. We will see that what it is. So, it actually sometime if the size is small, you might have to do a little bit of capping to bring it to the appropriate size, but then it has to be done in a standard manner. So, that is called capping. We will discuss some of them. Then standard testing, as normally we do for any other compressive uniaxial compressive strength test, we will do the testing, and this is what a core would look like after trimming, L by D. So, L is the length, D is the diameter, and factors, we have seen that factors affect the result is L by D, right. Obviously, concrete characteristic will affect, but L by D ratio is important. Now, why L by D ratio is important? The strength of cube is more than that of the cylinder, strength of cube, because the reason is when you are testing uniaxially a cylinder, let us say L, which is equals to D, and this is equals to D. So, you are applying compressive force like this from both sides. There is the basic, the basic tendency of this material would be, due to Poisson's effect, tendency of the material would be to expand laterally. And now, since these materials are basically bonded granular material, you have pieces of rocks or stones or aggregate, whatever we call it, and they are mechanically bonded, not really chemical bonding, mechanical bonded with the paste system, hardened paste system, right. Within the paste, of course, there is van der Waals kind of bond. So, that I will not come to, but these are weak bonds. Whatever bond between aggregate, very rarely it is chemical bond. If it is only some specific type of aggregate, volcanic source aggregate with silice, volcanic silice, some sort of chemical bond, very rarely it can have. Mostly it is mechanical bond. So, they are very weak in tension. You can push them all, they can withstand a lot of load, but you try to pull them, they separate out. So, what happens is, this is much less, this load carrying capacity or strength along this direction is much less tensile compared to this. So, you will have cracks of this kind, cube or cylinder failure, you will see cracks of this kind. But what happens is, when it is trying to expand, the machine plates here do not allow expansion. So, there is a frictional force like this, right. So, this is what we call as Platon effect, and this frictional force actually causes a biaxial effect, biaxial or triaxial effect in a way, this sort of. So, when you have a situation you are pushing from all sides, or two sides you are pushing, right, you are trying to push from this side, it cannot expand. As a result, you find in the failure pattern is something like this in case of L equals to D or cube. So, it is not L by D is usually 1 or 2, you can see that it is always dimension is very small compared to that required for buckling. Buckling occurs at L by D equals to short column, you might be knowing a much larger L by D value. So, this is not buckling, this is essentially because of what is called Platon effect, right. So, Platon effect causes failure. So, if your this effect, if you see knit stress would be, then there will be some compressive stress, there will be some compressive stress, from both these sides, and depending upon its length there will be a zone where there will be no compressive frictional forces due to compressive force due to friction of these plates. Plates offers friction, it does not allow to expand, but that vanishes off beyond certain point, and this is around root 3 by 2, around root 3 by 2, something of this order, root 3 by 2, one can show this forces So, when you have L by D is equals to 2, this effect will not be there, because this is now how much is this 0.8 or something. So, 0.8 L or some such thing 0.88 D. So, this effect is up to 0.8 D or something of that kind. So, if you have some value of D, I mean length greater than some value of 1.6 D or something, you do not have this effect. So, strength therefore, is a function of L by D. So, L by D generally recommended is 1 to 2, and correspondingly depending upon, now if it is less than 1, it tends to become too small and effects are much more prominent. So, the most standard cube test, I mean core test, when you do, L by D is restricted to 1 or 2. So, if you are getting less than 1, then you trim it off and put some capping material. Otherwise, try to keep it L by D equals to 1 and do it uncapped testing. Uncapped testing is the best, but not more than 2 again. If it is 2, although there is no benefit, because I mean there is no change, L by D effect really goes, but code restricts it to L by D equals to 2, because it is ease of calculation and things like that. So, L by D has an effect, L by D has effect on the L by D has an effect on the strength. Size effect, as I said, so minimum D should be 3 times the MSA. Minimum D should be 3 times the MSA, right, because then if it is MSA is maximum size of aggregate. Supposing he was using 20 mm aggregate, the D should be greater than 60 mm. Then you are getting a representative concrete sample, aggregates and mortar, everything will be inclusive. So, it is representative. If you test smaller than that size, then variation will be large. For example, instead of this, if you take 50 mm core, then you might have somewhere more mortar, less aggregate, or maybe more aggregate, less mortar. So, standard deviation will be larger. So, in such cases, what is suggested, that if you are testing small size core, you might test 9 cores instead of testing 3 cores with the appropriate size. So, test now, because you got to take care of the standard deviation, which will become high, and remember accuracy is sigma under root n. So, you got to increase it in that order, because it is a function of the number of samples required will be, to maintain same accuracy, number of samples required will be square, it is n square. So, n increases, n is equals to square of the error. So, if I keep the same, n would be e square, error square, so keep the same e, I need to 3 core, it will become 9 core, and so on. So, this is what it says to maintain. So, standard deviation actually tend to increase to take care of that kind of situation. This is been done. So, size is like that, size is like that. This is not really the size effect one understands in fractures. So, the another thing is direction of drilling, because casting is done in this manner from bottom to top. So, if you drill along this direction, there will be a layer effect, because failure is Poisson's effect along the transverse direction. So, this will be like that, right, layer effect. So, 8% higher results for vertically drilled core for layer effect. So, basically the strength, I mean you have a correction factor, we will see that correction factor, there is a correction factor, variation is around 8%. If you test it like this, drill the layer is something of this kind, then you will be testing with the layer in this manner. Horizontally drilled core, layers will be parallel to the direction of the load, right. So, this is how actually it will separate out, because failure is because of the transverse tension due to Poisson's effect. While you are doing vertically drilled core, the layer will be like this. So, results differ by around 8%, results differ by around 8%, right. Okay. So, vertically drilled core shows slightly higher results. So, correction factor is applied, which will actually multiplying factor is, there is a multiplying factor, we will see that how we do it. So, these are the other issues, related to coring, and one must know those. Now, IS code does not take this effect. So, end condition and capping, avoid capping, because as I said, when you put cap here, some material, supposing I put rubber, I put Teflon or rubber. which allows expansion easily, right. So, the frictional force which was resulting from the machine plates now can get reduced. So, it will fail at dual load. I said that Platen effect causes kind of a biaxial stresses from the other direction as well, confinement sort of thing, right, and this confinement reduces as I go down below. So, supposing I put now rubber will also expand with the plate. So, the confinement effect will get reduced. So, capping material has got an influence on the strength result you get. So, that is why it is standardized with sulfur concrete or high alumina cement, not any other cement or anything, because it is meant for comparing the results and there is a multiplying factor everywhere. So, basically standard capping material should be used, because it depends measured strength depends upon the capping material. If I have a very rigid material which does not allow which does not expand itself, rather it opposes the expansion of the concrete much, then you might find there is a confinement effect is more, then you might find a higher strength. If the confinement effect is less, you get lower strength. So, it is related to that. So, capping material has to be standardized. So, what you do is everything else is standardized except for the material that you have taken from the site. And obviously, if there is a reinforcement present, something like this, because it will not present along this direction, you are not going to drill along the reinforcement, that is very unlikely. It will be present, it is likely to be present somewhere in between, because while you are drilling vertically downward, a reinforcement might have come. Better to avoid them, but supposing if it has come, then you can actually apply a correction. So, that is what it is. Now, you can see this is the drilling machine, this is the drilling, this is the drilling machine, the coring is done. So, with a rotary drill, this is the bit, diamond bit. So, that is actually drilling, and that is how it is taken out, right. And this is the estimation of in situ strength. What you measure is the strength of the sample. From that I should be able to predict the in situ strength or equivalent cube strength. For example, if I have supposing I assume a hypothetical cube there, what would be its strength? Hypothetical cube, what will be that I call as in situ strength, because in situ strength is different than standard cube strength in the laboratory, which I prepare in a standard manner in the laboratory, cure it in a standard manner in the laboratory, test it after a fixed date, 28 days or whatever it is. This strength is different than in situ strength. In situ, so we call it in situ cube strength. What we get is in situ cube strength, right. Now, IS code gives you a way, I will come to that, but before that, this is from UK. So, they have done a lot of testing. For example, you can take core, and for the same concrete you take cubes also, right, cure them in the same manner, put it side by side. Well, yours a beam you cast, a beam, cure it and make some cube, cure them in side by side. Compaction procedure more or less you try to keep same, not the standard compaction, try to keep, so people have done this kind of tests and empirical equations they have come out with. So, for vertically drilled core, what they have found is F lambda is the measured strength, F lambda is the measured strength, and lambda is what? L by D, lambda is L by D. So, F lambda is the measured strength, and the in situ cube strength Fc will be given by 2.3 F lambda divided by 1.5 plus 1 by lambda. So, let us say lambda is equals to, okay, let us come. So, this vertically drilled core, horizontally drilled core, this value is something like this. In other words, what it is saying is, if you have a horizontally drilled core, let us say lambda equals to 1, in that case this value will be Fc will be equals to F lambda only, because this will be 1, this is 1, so this is 1, 2.5 will cancel out, so it is F lambda, Fc is F lambda. So, as long as it is taking a factor, this factor is taking into account what factor? The L by D effect it is taking, and then obviously the core size has to be large, that means the diameter must be greater than 3 times the maximum size of aggregate, and L by D lying between 1 to 2, and if it is 2, you can see that this will be 1.25 f lambda, f c is equals to 1.25, because standard cylinder L by D is 2. So, if it is 2, L by D equals to 2, then you get standard cylinder strength. If it is L by D is equals to 1, you get standard size, cube size, cube strength. So, that is what it is saying. So, this is how it is. Now, these factors are different for vertically drilled core and horizontally drilled core. If it is vertically drilled core, right, the multiplying factor, this factor is reduced down. That means, you are dividing it by some value, while horizontally drilled core is as good as a standard cube, because casting of cubes are done, casting of the cubes are done, casting of the cubes are done from bottom to top again. Casting of the cube is done. So, concrete is also done in the same manner. So, this is related to this sort of situations, right. Then if you are horizontally drilling it, actually horizontally drilling it, just a minute, I suppose this is correct, vertically and horizontally drilled core. Vertically drilled core is this, and horizontally drilled core is something like this. So, this layer effects are taken into account there. The multiplying factor is, there is a fractional, this is around 0.8 times, 8% difference. So, you can see that 2.5 into 0.92 or so will give you 2.3. So, that effect is taken into account for vertically drilled core and horizontally drilled core. Then you have got, they suggest that if you have a standard core, you want to find out standard cube strength, one suggestion is that multiply it by 1.3, but that is not the best way. So, 30% increase. So, 2.5 into 1.3, you get something like 3.25, close to this, and 2.3 into 1.3, you get around 3. So, for vertically drilled core, this is this, for horizontally drilled core, this is the scenario. So, in standard cube, but this is not to be used much. This is one of the suggestions, one can use this, but this is not really, the better ways are there which we will discuss. So, this is how you can find out from British considerations, while if you look at Indian scenario, okay, they also British Arstoil British code was using this formula, and they have also given a correction for reinforcement. So, reinforcement correction is given like this. You have say this is your core, L is here, D is there, and you have a reinforcement, here, which is at a distance h from the nearest face, this is h. So, this distance is h from the nearest face, and bar diameter, so R c is this is D, so twice R c. So, R b is the bar, sorry, this is R c, this is the core diameter. So, core diameter is R c, bar diameter is R b, the correction factor is 1.0, 1.5, R b into h divided by R c into L. So, this ratio R b by h by R c by L into 1.5, that is a correct additional factor. What happens when you have a reinforcement? It will fail at a lower load, because that interface will come into, and reinforcement is usually perpendicular to the direction of the loading, right, and it will split, move, the fracture would occur, it reduces down the measured strength. So, you have a multiplying factor which is more than 1. So, this is the correction, and if you have several reinforcement, this will be summed up simply 1.5 sigma, as many, supposing 2 bars are there. So, find out R b into h for first bar divided by R c into L, plus for the second bar whose diameter could be different. So, this is the correction factor, right. So, L is the unkept core length, h is the distance of the bar axis from nearer end, and etc., etc. So, this is the correction. Now, if you see in India, this is what it is. IS 456, what it gives you? It gives a correction for L by D, and using this L by D correction, you find out equivalent cylinder strength. Then it says that whatever strength you have got, multiply this by 1.25 to get equivalent cube strength. So, first find out the equivalent cylinder strength. How do you find out? Using this sort of a curve. There is a curve given in the code, L by D. So, L by D is equals to 2, this value is 1, that means you are finding same as cylinder strength. L by D is equals to 1, multiplying factor is 0.88. So, first you find out the equivalent cylinder strength. So, this is the correction factor which you find out from for your L by D, for your L by D you find out what is the correction factor. Then this multiplied by the measured strength F lambda into 1.25 will give you the equivalent in situ cube strength. So, first multiply by correction factor the strength that you have got, that is load divided by area and all that, multiplied by the correction factor, then multiplied by 1.25. So, that it does not take account of layer effect and those kind of thing any further. Now, if you have a correlation, such code test you can perform on in situ test you can perform, but then it is damaging. So, you do not perform too many code tests, you do at some places minimal you require, depending upon what is your objective. Now, you want to find out strength of, let us say, concrete columns in a large building. You cannot go on testing too many cores. So, what you can do is to increase, you can do code test limited, and correspondingly those locations you find out the rebound number. But before that you do ultrasonic pulse velocity test and ensure that your concrete is not has got sufficiently sound concrete, right. Velocity is more than 3 km per second. We will again discuss this in interpretation. Once this is sound concrete, internal core is okay, then you can take rebound number to predict the strength. So, to establish such a correlation, you need some limited code test to be done. So, such a correlation will be something like this. Say compressive strength estimation. Now, this is actually x axis is rebound number, x axis is rebound number, x axis is rebound number, this side is the strength, and then you have limited number of coring has been done. You can see that correlation do not come extraordinarily good, but if you have more number of samples, maybe the correlation improves. Yeah, it can be better, but no, this is here about I think some 5 plus 10 plus 12 13 results. So, if you have more, but then you go to do lot more coring actually. So, you can establish this kind of correlation and then from rebound number value predict the strength using this correlation. So, do an extensive rebound hammer test all over the place, you will get several values and correspondingly from this you estimate using this kind of equation. You use find out the estimate the strength. The strength variation will be plus minus 20%. Error would be easily, it's suggested that error can be of the order of around plus minus 20%. So, if you say FCK is equals to 20, it can be anything from 16 to 24, it can be anything from 16 to 24, right. So, that is what we do, estimate the strength using code test. Now, you can actually in precast, if you have a casting yard, something like railway sleeper or something like electric pole, and you have a precast units and you want to test them, then you can establish a multiple regression or correlation. You can actually use both rebound hammer and ultrasonic pulse velocity test and establish correlation curves. For example, this side is pulse velocity, this side is rebound number, right, and these are the strength contour lines. So, this is 40 MPa, this is 15 MPa and so on. So, you can actually have two variable regression lines generated and then you can use them in quality control. So, for example, if your rebound pulse velocity is 4 and rebound number is 37, from this kind of graph the strength is likely to be in situ strength measured actual strength is likely to be close to 25 MPa or so. But this these values are not universal, you have to find out for specific concrete. Okay. So, you can actually establish your quality control system using this.